Teacher Avanasa here. Welcome to today's super special Evan Measure Theory class. As the ruler of the Phantasmoon games, when it comes to measuring things, I am undoubtedly the expert. I mean, I do have this certified ruler of mine after all. Apparently, Aha thought it would be funny if I taught you a little something about measure. Now, you might be wondering, what in the Aha do you measure with measure theory? Is it length? Area? Or maybe volumes? Trivial! Way too trivial! Don't you agree, Labubu? Today, let's learn how to measure even the most ridiculous math objects imaginable. Whether they are finite or infinite, countable or uncountable. But before we start, we have to start at the very start. A set theory. What is a set? In math, a set is a collection of objects. For example, I want to make a set of the fluffy across the blue characters. So, this set has elements: baseball, raccoon, March bunny, woof woof den, standoff, Himika, and Mr. Yang. This type of set is called a finite countable set. Another type of set is an infinite countable set. For example, the set of natural numbers 1, 2, 3, 4, and so on. With this infinite life of mine, I can count the elements of an infinite countable set. We also have uncountable sets. These are usually in the form of intervals of real numbers. For example, take the closed interval of 0 and 1. Let's count together, Babubu. 0. 0.1? No, wait. 0.01? What about 0.001? The point is, even with my infinite lifespan, you still can't count the elements of an uncountable set. Let us define a universal set as omega, which contains all the elements we're interested in. In that case, let's have our fluffy universe as our omega. Let us have set A like this and set B like this, both being subsets of omega. Now, we shall learn all kinds of set operations. First, the complement of set A is a set of all elements not in set A, but still in omega. If all elements of A are also elements of B, we can call set A as a subset of B. If B is a subset of B accent, and B accent is a subset of B, then B and B accent are said to be equal. Now, let's define new sets of A and B. The set of all elements which belong to either A or B is called the set of A union B. The set of all elements which belong to both A and B is called the set of A intersection B. In particular, if the intersection of both sets is an empty set, then set A and B is said to be disjoint. Now, little raccoon, there is one important law in set theory, Team Oregon's law. It may sound scary, but it's just a rule explaining how unions and intersections interact under complements. Let's use our fluffy universe again. Suppose that set A is baseball, raccoon, and March bunny, while set B is March bunny and woof woof dan. Then, our union B contains everyone who is in either A or B. Now, take the complement. That is Himika, Mr. Yang, and Sundov. Notice that the complement of A is Woof Woof Dan, Himika, Mr. Yang, and Sundov, while the complement of B is Baseball Raccoon, Himika, Mr. Yang, and Sundov. So their intersection, where everyone who is neither in A nor in B, is Himika, Mr. Yang, and Sundov. Did you see that? This matches our previous complement of the union. Can you guess what that means, Labubu? Yes? They're equal! This is the first Team Oregon's law. The second law works similarly. Let's draw it! This is the intersection of A and B. The set where its element is not in both sets is equal to sets where its element is missing from at least one set. Now, suppose we have a collection of sets in omega. Let's call it the class
A.
For example, we can make a class from subsets of our fluffy universe like so. Some of this
A.
is more special than the others. If we perform a certain operation on Setsuna
A.
and the result is still in,
A.
we say that
A.
is closed under that operation. A field is a class that is closed under complementation, then finite intersection. What's a finite intersection, you ask? Basically, you intersect a finite amount of sets in
A.
like 2, 3, 4, 5, 6, or even 100 sets, but still finite. Using mathematical induction, we can prove that if
A.
is closed under pairwise intersection, then
A.
is also closed under finite intersection. As a consequence, a field is also closed under finite union, thanks to De Morgan's law. Last but not least, every field also must contain the empty set in omega. In fact, a class that only contains the empty set in omega is a field called the degenerate or trivial field. A sigma field is a special type of field. Basically, a field that is closed under countable intersections and countable unions is called a sigma field. By countable, I mean both finite and infinite countable. Remember that the set of natural numbers is countable. So, if we perform intersections of sets indexed from 1 to infinity, that's infinitely many yet countable. The result must still belong to the sigma field. This is what closed under countable intersection means. Just because a class is closed under finite operations doesn't mean that it is also closed under countable operations. Can you think of an example, Labubu? Okay, here's an example. Let
A.
be the class of open intervals of the form 1 minus 1 over n to 2. The finite intersection of sets in
A.
is also in the form of this open interval, thus
A.
closed under finite intersection. Now, if we try to perform countable intersection of sets belonging in,
A.
we obtain a left closed interval from 1 to 2, which by definition is not a set in
A.
Therefore, we know that
A.
is not closed under countable intersection. A sigma field has all the properties of a field. In fact, if
A.
there's a field that contains only finitely many sets, then
A.
it's automatically a sigma field too. Any set lucky enough to belong to a sigma field is called a measurable set. So, what in the aha is the deal with measuring sets? That'd
A.
be a sigma field generated by a class of sets. A measure is a map from a set in
A.
to the real number. Of course, this map must satisfy some particular conditions. The measure of an empty set is by definition 0. Therefore, since any set is bigger than an empty set, the measure of any set belonging to
A.
must be non-negative. And last, for any countable collections of pairwise disjoint sets in
A.
the measure of their union is equal to the sum of their individual measure. In other words, measuring them all at once, or one by one then adding them together, must give the same result. We can measure any measurable sets however we want. Size is relative, after all. Example, for a countable finite set, its measure could be its cardinality, or the number of elements in the set. For an uncountable set like an interval in a real number, we can measure it by the length of its interval, or the value of the integral of some function over the interval. If the set is an event, then its measure could be the probability of such an event occurring. Alright, that marks the end for today's lesson. Next time, let's learn even more properties of fields, sigma fields, and measures. And perhaps how to construct them with me. Hope you learned something new. Little Waku?